Okay, so today, or last time, I should say, we talked about linear algebra and sort of the route to regression, and then also connections to optimization, and how optimization really sort of like ties together many of the sort of computational tasks that we do in data-driven modeling or analysis. So today we'll talk a bit more about how we go from regression and then some optimization techniques. This is going to be sort of a high-level overview of techniques. I'm not going to, again, get deep into the specific methods. I'm not going to say you have to use this one or that one for anything, but I think it's worth having a view of some optimization techniques, because I think it's something that's not really covered in general. And I think it's not just something that's good to like know how to do, but it's good to know how to think about. And as we'll see, a lot of optimization techniques are just like stuff some guy came up with. And sort of with respect to that, optimization is often uniquely tied to the problem you want to solve. So my hope is seeing a broad level overview means that you can, when you encounter new problems, can choose different techniques. So again, homework 1 is due today. Just push it to your GitHub. I'm not going to check. I mean, I probably won't grade until probably next Tuesday, so it is what it is. If you have trouble submitting it, you can email it to me. You can submit it on D2L for this first one. We'll figure it out. But if you can, try to submit it on your personal fork of your course materials. Does that work for everyone? Again, I'm flexible.
If you want us to put it in the assignment folder that you created, or make our own folder.
How has everyone done it? Who has started it, done it so far?
I just have it in assignments. I just made it a folder, and it's like assignment 1 _ Flanagan. And I have like an input file, and then I have like the IP YMB.
Yeah, I just created a separate folder called homework, but maybe you want to consistent.
Yeah, it would be nice to be consistent. That way I can find it. I would kind of prefer just having a separate homework, separate from the assignments. That way I can easily translate this to a future class.
Is it okay in a Jupyter notebook?
Absolutely. Any format you want.
Okay.
Any common format you want, like notebook, markdown file. If you want to submit it as PDF, I'm totally happy with that. For the most part, I'm not going to be running your code for this class because it's not going to be like a, did you get the right answer or not? Like there will be very few cases in this class where the code has to either be right or wrong. It's going to be more about your analysis. So yeah, I would prefer if you could make it just in your code space or in your repo, just a separate homework folder, and put all of your files in there, and I can figure it out from there. It doesn't have to be super standardized. There's only 10 of you or so. So I can just, as long as I can pull your repos, we'll be good. Cool. And if there are problems, I will alert you to them. Okay, cool. One thing that I realized I wanted to mention, oh geez, got all messed up. Hopefully the rest of the slides aren't like this. One thing I wanted to mention last time that I forgot to, the first line and the last line are the most important. Composition of linear maps is just a linear map, right? And this is why I was stressing that concept of the span of your linear space. So I can say this because I know what it says, and I'll fix it before when I post the slides. But if you have a vector space V and a vector within it, and you have 2 linear maps, this is supposed to be both F and G mapped from the space V to W. You can kind of see it in here. Then the composition of those maps also maps from V to W. It does not go to a new vector space. So that means that there exists a function or another linear map K that also maps from V to W, which is simply the composition of these maps. Sort of conceptually, what this means is linear maps cannot take you outside the span of their respective vector spaces or the functions that are applied to them. this is going to be important when we move to deep learning in particular, and hopefully will let you avoid one fundamental problem that I've seen many people take, which is not applying activation functions to their networks, which is just wasted computation. So we'll return to that when we get there. I just wanted to state that, because while linear algebra is one of the sort of foundational things, it is very limited in its modeling capabilities. So we need to know what those limitations are. And linear maps only can produce linear maps. Okay. All right, so back to regression. We have our classic system, AX equals B. For the most part, what we analyze in our simple math classes is square systems, but if you now watched that video that I posted and what we talked about, most of the time what we're really working with in science and engineering, and kind of any real field with data, is an overdetermined or underdetermined system. So overdetermined systems are ones where the A matrix is tall and skinny, which means that we have basically many more kind of observation, or many more system terms than we have observations. And in general, those have no solution unless you add constraints. On the other hand, underdetermined, we have many more unknowns, and we have many ways to satisfy the system of equations. In fact, infinite. So in general, if we want to work with systems of this nature, we have to do something to solve these. And so for overdetermined systems, what you do is you add constraints, which are of the function or of the form some function g. This would be like, I don't want to violate mass or energy conservation, or I want to minimize travel time, or I want to XYZ. This is something that we as scientists and engineers add to the system to say, like, this is what I think it should do, or this is what I want it to do. And then we solve the problem like that. On the other hand, for underdetermined systems, we have to basically minimize some error, and that's all this is saying. G is our error function in this term. So here, G is a constraint. Here, it's an error function. And in this case, what I've written is the 2 norm. We talked about those norms last time. And basically, we want the norm to be less than some value, ideally minimum. So this is what we do. But we can, and as I mentioned, we're starting to move beyond the linear systems. So we can more generally write, instead of the 2 norm, we can just write these terms as some generic function. It can be any function, and this is sort of the framework that you can think about all forms of regression in. And so in general, F will be nonlinear, and we can't solve linear or nonlinear systems in general. Like, there are some specific cases. And in fact, many nonlinear systems have either no solution or infinite solutions, as we mentioned with the over and underdetermined problem. It's slightly different, but another case. It seems that in math, there's sort of 3 cases that you find yourself in. There's no solution, there's one solution, or there's infinite solutions. Those are the most common cases. So that's true of nonlinear systems and both under and overdetermined systems. Okay, so just to remind you of that idea of norms, because this is our error function, right? Something that I want to stress, and I will stress this again at the end of this lecture, but the metric makes the model, right? That function f is our model, right? The error term g or whatever, here we'll call it e as a more intuitive thing. When we do optimization, if there's infinite solutions, the metric that you choose to optimize and the model both affect what solution you end up getting. They're not independent. And I think that's something that I'm sure you've heard before, but everyone needs to hear probably a couple times a year. So just looking at this set of simple sort of data points here, it's basically linear with some noise on it. If you fit some linear models and you use the different error norms, so we have our MAE, MSE, and then this max error norm. For this case, where they're all pretty nicely aligned, like this is a pretty much linear system. They all fit relatively closely together, but there are some differences, right? If only our data looks like that. So here's a simple case on the bottom plot here where there is one outlier, and this is where, and this should be intuitive to you. The MAE and MSE both produce lines that we could quibble about which one is better, but are both reasonable for most of the data points, but they miss the outlier. And as you'd expect, the max norm, where you're trying to reduce your maximum error, it's going to fit sort of in between the bulk of the data and that one outlier, right? Okay. And so this is something that you should think about as you choose error metrics, is the distribution of your data and what you want to actually be able to model well. Of course, this is a linear model, so it's a bit boring. Okay, so if we go back to talking about these underdetermined systems, which is like almost always the case in earth and environmental sciences, like we have a lot more things in our system than we can measure. So we need to find the minimum error for our given model. And this brings us to the world of optimization, where we have to take some iterative approach. So this is sort of the general design, or the general workflow for an optimization. It's just a loop, right? Like we start with our design specifications. In this case, it's coming up with a model, or what we think is something reasonable that we can use. You start with some initial guess of like, this is how it could work. And then you evaluate performance and you loop until you get to something that is good. For the most part, in our models, what we optimize is parameters. There are other things that you could optimize, but I'm not going to get into things like structural design or anything like that. We'll mainly be talking about optimization of what we call parameters. Okay, so broadly speaking, there are many ways to classify. Like there's no like systematic sort of framework that is a complete classification of optimization techniques. So I'm going to mainly talk about two types, but if you search optimization classification, you'll get all kinds of different classification schemes. But I think this one is generally decent. So when we're optimizing, we're looking for an extremum of some function, which is our model. So we either want a maximum or a minimum. We always frame it as a minimum, which could just be negative of the maximum. No problem there. So the three that they chose in this particular figure, I think is generally pretty good. There's like local greedy searches, which is mostly what I'm going to lump these two into black box techniques, which are derivative free. But local greedy searches, where you kind of just like look around you and choose the best you can. Evolutionary algorithms, I'll talk about in a second. And then there's sort of more classical numerical methods, which are all going to be basically derivative based. I guess bisection method is technically not, but we're not going to talk about bisection method too much. Okay, so in the black box, I'll show you coordinate search, hook Jeeves, and these evolutionary algorithms. And then on the gradient base, we'll talk about gradient descent, Newton's method, and Adam. We'll return to Adam and other sort of more modern optimization techniques for machine learning when we get there in a couple weeks. I assume everyone's at least seen gradient descent and Newton's method, right? Okay. Yeah, so again, this, we're sort of still in the zone where I just want to make sure everyone has the right terminology and stuff, so.
Newton's the Newton-Raphson.
Yeah, Newton-Raphson, yeah, exactly. So we may be able to breeze through this and you might be able to get out a little early on Friday then, but, okay. So, I think it's good to just know some of these, that way you can think about solving different problems with them, because applying Newton's method to everything does not work. Newton's method is very challenging to implement. So just going over those optimization techniques, coordinate search is like, if you ask like, probably not a 5-year-old, but a 10-year-old what to do, this is probably what they would come up with. You know, like they don't have this they might say like walk downhill, but if you like ask like how, they don't have this concept of derivatives or anything. So this is kind of like the most obvious thing that you could do with when you don't need derivatives. And for a 2D system, really all you do here is you look in one of your coordinate directions and you do a line search. You just look until you hit a minimum, and then you step that far. So that's here shown, like if we go in the X direction, we search until this kind of hits that minimum there, and we say, okay, that's as far as I'm going to go. Then you turn 90 degrees, or whatever respective thing that is in your coordinate system, and you do the same thing again. Very obvious, like very easy to do. So it's just these two equations that you iterate over in a while loop until you hit some desired tolerance, right? Very easy. Things can go wrong with this, of course. So here's an example of one where you hit a local minima. It's not even necessarily a local minima. It's just where you're in well, I guess it's kind of a saddle point of sort. So where both of your coordinate directions are uphill, but there is still a downhill that's not along the coordinate direction, right? So this is a failure point, but this is something that's very easy to implement and very easy to think about. For 2 dimensions especially, that's great. One thing, yeah, I'll say it now. One thing that I think doesn't get, that things like this don't get enough credit for is in 2-dimensional space, these saddle points or whatever are very easy to run into, or very easy to get yourself stuck in. For very high dimensional points or systems, almost every point is a saddle point. So that's something to be aware of. We'll come back to that when we talk about deep learning as well. So if you wanted to get out of that sort of issue, well, no, this doesn't get out of that issue. If you wanted to take a slightly, maybe more flexible approach, what you can use is this Hooke-Jeeves method. And basically now, instead of specifying exactly which direction you're going and going until you hit a minimum, you say, I will take a step in every direction and choose the best one. So Hooke-Jeeves versus coordinate search is really sort of this trade-off of either fixing your step size and trying every direction versus trying one direction and varying your step size. And so what you do here is you take your coordinate directions, you try every point with some fixed step size, you choose the best one, you iterate, you do the same thing, you end up here, and now here, every step is bad, right? So when you hit this case, what you do is you shrink your search direction. And then, if, and in this case, it's going to be true that these are all bad steps, you would do that again. And again, you do this in a while loop and you continue to either take a step when you find something better or shrink your search region until you converge or can't find anything, right?
What if you have 2 values that are practically identical, like with whatever degree of like accuracy you have access to? How do you choose a point in that case?
Well, this is kind of where I meant like most optimization algorithms are just like someone like thought about it and was like, wouldn't it be nice if we just did this? So often techniques where you have equivalent things, you either choose randomly or you try both and then you find which one is better. It depends how computationally complex you want to get, but for the most part, they're heuristics. Like there's not like a mathematical framework for deciding between 2 points, especially for black box methods. For gradient-based methods, you can start to like add on higher levels of derivatives and stuff and choose more desirable sort of slopes or curvatures or things like that. But for black box methods, they're very simple, right? They're almost entirely heuristic based. Like we're going to try this and we're going to keep doing it until we're done. Any other questions on these two? They're fairly simple and obvious, but they're worth knowing about. Evolutionary algorithms go in this sort of entirely different direction, and the coordinate search and Hooke-Greaves are like specific algorithms. I'm throwing all evolutionary algorithms into one bucket because we could spend a whole class on them. But the general idea of them is all sort of the same. And you would never use an evolutionary algorithm for like a 2D system. You generally only use them for higher dimensional systems where like if you have like, you know, if you have like 40 dimensions or 40 parameters that you want to optimize, you get almost nowhere with this, right? Because you have to take 40 steps before you circle back around and optimize your first parameter again. So evolutionary algorithms are generally speaking better for high dimensional systems, and especially systems where taking derivatives, which we'll talk about in the next slide, is very challenging. And they're basically stochastic methods at their core, where you start by drawing some random sample of parameters from some hopefully plausible space. You draw those parameters. You generally use, you can do ones where it's just single at a time, but like things like particle swarm optimization is one technique where you sample a bunch of them and then you try and say, okay, well, which of these are good? Evaluate, find your best fit, exclude some of your bad selections, and then you sample again. And then you repeat until either the distribution collapses or you find the criteria that you want. And the sampling distributions, the update step, all of that is going to be algorithm specific. So there's like basic evolutionary stuff that's more like single updates. There's, as I mentioned, this is sort of particle swarm as it's the figure there. And then in hydrology, shuffled complex evolution is sort of historically the standard when it comes to optimization or calibration. So I'll have you really gotta stop punching the TV. So I'll have you learn more about that in your second homework. And it's often referred to as SCUA because it was actually developed here at University of Arizona. Yeah. Wow.
Was it developed in this department?
Yes. Yeah, Ocean was. Yep. So you know, it's kind of fun to learn about that, and it's still like practically speaking, probably the most commonly used optimization or calibration algorithm in hydrology.
And it's called shuffled complex evolution.
Yep.
You Arizona.
You got it. Yeah. Straight to jail otherwise.
It's not SCE Wildcat. You gotta get the UA.
I know. They just
Yeah.
dash Ocean.
I always find that funny, but in a lot of software packages, it will be implemented as that.
Did you say it's popular in hydrology? Do you have any theories why it's not popular in hydrology?
Because it was developed in hydrology. Other fields do use it. It's fairly well known, but close the door a little bit more. No, I'm kidding. I think it wasn't until probably the last 20 to 30 years that I think hydrologists started to look outside the field for a lot more mathematical techniques. And I think there's a long legacy of things that we could have done better on. Optimization and calibration is one. I think the fact that, and I didn't even mention this, I keep saying optimization. Calibration is just optimization, right? For those of you who have done it. I think sort of hydrology as a field sort of came up with a lot of its own terminology and got kind of insular. And I think that led to a lot of low-hanging fruit being left on the table, which is kind of, yeah, for better or for worse, a legacy of the field. But I mean, SE does genuinely work, so I'm not like trying to say it's a bad algorithm or anything like that. But by and large, yeah, I think hydrology and computational hydrology and modeling has been fairly insular. Anyway, gradient-based methods. So obviously the first one is gradient descent. And it looks like this, you walk downhill. It's very, very conceptually easy. All you have to do, and I should say, this is like the starting point for all of deep learning. So you gotta know it. Again, we're trying to find an extremum, which basically means that the gradient of your function is 0. I should note that that's necessary but not sufficient criteria, which I'll return to in our last slide, where we can talk a little bit more conceptually and have a bit more discussion. But if you want to do this, all you do is you start at some point, x of k, you calculate the derivative with respect to the function that you're doing, and then you walk downhill, hence the negative sign, with some amount of speed delta. And that updates your new position, and you just repeat that until you get to the bottom or you explode. So very easy. However, I should say this does require you are able to calculate the derivative of your function. That's like fundamentally the thing that you need to be able to do for all of these methods. This, you know, this intuitive picture is nice and makes it seem like, you know, that's all good. This does, as you can imagine, if you're taking just one derivative, this is a linear approximation to your function at any given point, right? You're just checking the slope at that point. So you're ignoring any curvature or any other features of your function. So obviously you can go to higher order methods. And I do want to just make sure I highlight this. This deep learning, this solving PDEs or ODEs, almost entirely is sort of the differentiator. Not entirely, but for the most part, Newton's method is, if you're doing finite difference, is sort of your starting point for most ODE or PDE methods. It's not always the right choice. And especially in its vanilla form, it's almost always the wrong choice, but we're not going to get into that. So instead of relying on the linear estimate, and again, this is the exact same formula, or is derived in the exact same way. If you want to do gradient descent, you approximate your function like this and you do it. If you want to do Newton's method, you take a quadratic form, which means you take the second derivative with the Taylor expansion, and that's how you approximate your next steps. So these are the update steps where this is it. So it's, you take your point, and then it's the ratio of the first and second derivatives. And what you're doing there, if you're taking a first order method, your downhill step is in this sort of direction. And if you think about it, second order means parabola, right? Second power. What you do in Newton's method is you approximate your function as a parabola with the right slope at that given point, and then you go to the minimum, right? And then you just repeat that until you're done. I mean, you don't go to this point, you go to the actual function evaluation, but that's how you find the minimum, because we can exactly solve the equation there, right? Newton's method has all sorts of problems. Like you can find yourself in um, areas where it will diverge if you have a bad first guess. And so there are many forms of add-ons that you do with it to solve harder problems, but this is the concept, and that's what I want you to know. But I also want you to know that implementing Newton's method without any of the add-ons, like trust regions and things like that, is probably going to cause you numerical problems. Okay, so much like the black box methods, where it's just kind of like you can think about it and be like, well, what if we did this instead? You can do that with these gradient-based methods as well. You can tack on all sorts of things, and a lot of like the black box methods, these sort of additional pieces can be added and, generally speaking, shown empirically to help, but maybe not rigorously mathematically. Do we always understand the full, convergence criteria and stuff? And I should say that's also true of things like evolutionary algorithms and even these other simple these we probably know pretty well. But for the most part, black box methods don't always have super hard bounds. Things like gradient descent and Newton's method, we have very rigorous bounds. When you start adding on some of these more conceptual ideas for optimizers, they start to get a little bit fuzzier, but if you can show empirically they work, most people are happy. As I'm sure many of you know, Atom is kind of like the default optimizer that's used across all of machine learning or deep learning in general. And Atom in particular adds two concepts together. The idea of momentum. So just regular gradient descent, if you have a relatively shallow or not steep area, your optimizer gets really stuck. So adding momentum helps you traverse very flat regions. And then Atom also adds what I'm calling a quasi second order effect. So it approximates the second derivative, but it doesn't actually calculate it. So it uses running statistics of its past history to sort of estimate what that second derivative is. And we'll talk more in depth about these later, but just showing there are many different versions of this. So stochastic gradient descent is just like gradient descent with noise. You can add momentum. Adagrad, I can't quite remember what it does. RMS prop is sort of the precursor to Atom, where they started taking on these second order effects. I'm sure Adagrad just had a better version of momentum or something. Does anyone know Adagrad? Doesn't matter. But they all have different characteristics, but for the most part, people just use Atom at this point, and with some additional add-ons. With that, who here has trained a neural network before in general? Pretty much everyone. Okay. So we'll return to this later, but it's not too important. Okay, so at this point, I would like to think about optimization. And I want to add two things, and then we can have a little bit of discussion, and I'll let you out. 1 and 2D cases are very easy to visualize and think about, and they're useful for sort of developing taxonomies. So again, you probably all know about things like global versus local minima, inflection points and stuff. They're really useful for developing those taxonomies, and same with 2 dimensions, where we can have our, a local maxima, a saddle point, or a bowl. And for the most part, the models that we'll develop later in this class are going to be higher dimensional. And I really like this quote from Geoffrey Hinton. To deal with hyperplanes in a 14-dimensional space, visualize a 3-dimensional space and say 14 to yourself very loud. High-dimensional spaces are hard to think about. And again, the point that I think I want to make sure to make is as I already said, your metric and your model are both linked. The third part of realistically any model is your optimizer. All three of them are completely interdependent. And, we say we have different methods for things, but in practice, when you implement something, they're all linked and you can't really disentangle them. So that was where I wanted to get to today. And then I just wanted to talk about thinking through these ideas of error and optimization and how you all think about it. So I'll stop the recording there so we can